Okay. Good morning. I'm Tuomas Sandholm, and I'd like to talk to you about some of the current research that we're doing in my lab. I'm Dunhill Jordan University Professor of Computer Science and founder and director of the Electronic Marketplaces Lab and co-director of CMU AI. And I'm in the computer science department, but also in MLD, in the algorithms, combinatorics and optimization, and the CompIO programs. So some research perspectives on what we do in my lab. So mainly we do optimization and game theory, and a lot of things also in the intersection of optimization and game theory. On the optimization side, we do a lot of integer programming, stochastic optimization with integer variables also, and also convex optimization, especially when it comes to equilibrium finding in games. We like to select research topics that are of high real-world impact. So I think about the world like there are infinitely many interesting research topics, but only a tiny fraction of them will ever have real-world impact. But at the intersection of what's interesting and will have high real-world impact, there are also infinitely many topics. So we try to pick topics in that intersection. We do kind of a full spectrum of research approaches. So starting from new concepts, like what could AI, what could computers do, and so on, and what kind of new market designs could there be? How could we make the world a better place? Then to theory, to experiments, and large-scale fielding. And while this line here on a slide looks like it's a pipeline, kind of a water flow, it's actually very iterative. So when we do fielding of systems, that gives us new ideas for new concepts, new theoretical questions, new experimental questions, and so forth. One example is leveraging increasing computing power to increase economic efficiency. And one example therein is running more complex mechanisms. For example, we have done a lot of work, much of the early work also in combinatorial markets, like combinatorial auctions and generalizations thereof. And that's something where we really did conceptual work, like introduced multi-agent preference elicitation, introduced structured bidding languages, and so on, to theory, to experiments, to large-scale fielding, all the way actually to a startup company where we fielded 800 of the most combinatorial auctions ever conducted, totaling $60 billion. And yes, that's with a B, not with an M. Another example is capitalizing on the piles of information that are around for use in markets. So, for example, automated mechanism design. Typically, when people do mechanism design, which is designing the rules of a game so good things happen, for some definition of good, that's a manual endeavor. But in many areas, especially these highly multidimensional mechanism design problems like revenue maximization, the field had kind of gotten stuck for 40 years. So the optimal revenue maximizing single item auction was figured out in 1981, but since then, nobody has figured out how to even sell 2 items so as to maximize revenue. And we showed that there's actually computational reasons for that, and we are doing a lot of work on computational approaches to mechanism design. Now, in the rest of this talk, let me tell you about 4 of the current projects in my lab, and I might have an opening for a student in my lab this fall. I'm not sure yet, but I'm happy to talk to any of you about that possibility and learn to know you. The first is kidney exchange. So my group's algorithms run the National Kidney Exchange for the United Network for Organ Sharing, and we have been live since 2010. Every week, our AI makes a transplant plan for 80% of the transplant centers in the US. And there's a lot of new research to be done here. So let me start from the basics of kidney exchange. So the main idea is that there aren't enough kidneys to go around from deceased people. Not enough people are organ donors. So that's where you do live donation. So I could give my kidney to Reina. In principle, if she needs one, and I'll be fine with one, but in reality, I probably can't due to tissue type and blood type incompatibility. And that's where kidney exchange comes in. And at the simplest, it is swapping donors. So here we have on the slide these rectangles, which we'll call pairs. Each pair has a donor and a patient, and they're incompatible. But if donor 1 were to give to patient 2, and donor 2 would give to patient 1, then both patients could live. And if you think about these rectangles as nodes in a graph, so not the green circles, but the rectangles, this would be a 2 cycle. And you can also do somewhat longer cycles. For logistical reasons, you can't do typically longer than 3. And this becomes a very hard problem because it's no longer matching. Then it's an NP hard problem, as we proved. And we also introduced this idea of never-ending altruistic donor chains, where you have some altruist donor that doesn't expect anything in return, and they start chain. And at the end of the chain, there's a leftover kidney inside a donor still. And then in the next week's batch, we can pretend that they're the altruist, and this gift keeps going forever. This has actually surpassed cycles as the main modality of kidney exchange today, and around 10,000 people in the world have gotten kidney transplants using these never-ending altruistic donor chains that we invented. Now, there's a lot of work to do on this still. One of the interesting open questions is dynamic kidney exchange. So instead of optimizing every week as if it is the last, we might want to save some of the pairs or some of the altruists for the future, so as to get more and better matches by keeping liquidity in the pool. But how do you do that? Who do you match now? Who do you save for the future? And so on. Well, that's where we do automated policy optimization. And we have this framework called Future Match, where we separate the means and the ends, first of all. So typically when people talk about what should be done, they confound the means and the ends. And here we cleanly separate them out. So the humans say, what is the goal of the kidney exchange? Is it to match as many patients as possible? Is it to increase life expectancy as much as possible overall in the pool? Is it, and how do we weigh in favoring highly sensitized patients and pediatric patients and so on? But we don't want the humans meddling in exactly in this situation, you should match that type of person to that type of person and so on, because that is very difficult for humans to do. So we take from experts the goal, and then we take historical data. So for example, we took the data as to how much more life extension you get with a perfect tissue type match than without. And this is something that had been debated on phone calls by humans as to how many points should be given for that and so forth. We said, no, we just use machine learning to figure out what is really the value of that for the given objective. And that kind of took the philosophizing and debating of the table and let data really tell you what should be done. And then we learn, based on the goal, what value should be given to different edges, and we'll also learn what potentials should be given to different graph elements. So what would be the value of this graph element in the future if we didn't match them today? And a graph element could be as simple as a vertex, but it could be bigger elements as well. And once we've learned that offline, then in our online matching, when the actual problem is faced this week, we find the vertex disjoint combination of cycles and chains that maximizes the objective. So now the future is automatically captured and baked into the myopic optimization. So that's kidney exchange, lots of other things to do there as well. And I'm starting a new project on using such policy optimization techniques for deceased donor heart allocation as well. There's been a lot of change in the heart allocation policy in the US, and people have very different opinions as to what's good, what's bad, and it's been fairly manual. in terms of the design. So now there's a real opportunity to use AI and supercomputing again, but now for hard allocation. Another project in my lab is solving multi-step imperfect information games. And most real-world settings are imperfect information games and require, therefore, totally different techniques than what you see, for example, for chess or for Go. The main benchmark has been No Limit Texas Hold'em, and we are the multi-time world champions in that game, in AI to AI competition. And then our AI Librados in 2017 beat the best humans at that game. And last year, our AI Pluribus beat the best humans in the multiplayer poker. So there's lots to do there. I'm just going to mention 3 threads here out of many threads that we're working on. One is abstraction algorithms with bounds. So games have this abstraction pathology that as you make a finer grained abstraction, you may actually get worse solutions, more exploitable strategies. Despite that, we show that you can actually do lossy abstraction with bounds. And we've developed a fairly general mathematical abstraction framework that actually gives exponentially tighter bounds than prior approaches to abstraction. But the best practical abstraction algorithms, which also currently come from my lab, they don't fall into that framework. So we need to either extend the theory or change the algorithms, or probably a little bit of both to marry up the theory with the practice. Another thread, let me jump to the next green bullet here, is depth-limited subgame solving in imperfect information games. So as you probably have seen in your undergraduate AI classes in perfect information games, game tree search starts from the current situation, looks ahead a certain number of steps, maybe a varying number of steps, and then an evaluation function is applied to evaluate a partial solution. In imperfect information games, that doesn't work. Imperfect information games have these information sets that cut across subtrees, and you have to balance your strategy across those nodes in the information set. For example, in poker, you can't always bet your good hands and call your bad hands. That would be way too transparent. Now there's been great progress over the last 4 years in actually making depth-limited subgame solving in imperfect information games possible. And subgame solving means that you don't start from the root of the game, and depth-limited means that you actually don't go in your search all the way to the leaf. Both of those are hard, and we can do them now, but there's a lot of additional work to do. And the third green bullet on this slide is games with simulator access only. So typically in game solving, we're given the game, given the rules of the game. But what if you have simulator access only? So you could just try playing it and see what happens. Well, in AI, typically that has been solved or addressed by reinforcement learning, and game theoretic techniques have not been able to apply there. Now, reinforcement learning doesn't give any exploitability guarantees, and oftentimes those solutions are frail. So even if humans lose to them one time, once humans play with them a little bit, they learn how to beat them. Game theory, on the other hand, generates unbeatable strategies, but that hasn't been possible with simulator access only. And now we have the first 2 new directions how that's actually possible. Very exciting new stuff, but very nascent also. So a lot of work to do to make that scalable. Next topic, third project out of 4 that I'm going to mention is what I call biological steering. So it's computational game theoretic equilibrium finding and opponent exploitation techniques for steering evolution and biological adaptation. The idea is that living organisms evolve and adapt to challenges, and that's a key difficulty in developing therapies since the challenged organisms develop resistance. The idea then is to harness evolution and adaptation strategically for therapeutic or technical or other goals. The idea is that we model this as a 2-player incomplete information extensive form game between a treater or controller and a disease. And then we have a couple of different approaches. How do we actually compute steering plans or treatment plans in this game? One is to find a Nash equilibrium or a near Nash equilibrium or a more refined a strategy according to refinement of Nash equilibrium. And this is kind of using the types of things that we have developed in poker, which have become very scalable. Now, that is safe in that in zero-sum games like this, even if the opponent doesn't play rationally, we are safe. On the other hand, it is very conservative, and maybe too conservative. And that's where the second approach comes in, which is opponent exploitation techniques. So if for parts of the state space, we have good knowledge about how the adversary will behave, then we don't have to take the game theoretic worst case assumption in those parts of the search space. And we can use techniques like deep reinforcement learning and so on. And the third approach, which is really a sub-approach of approach 2, is that the biological opponents can't look ahead. They don't even have a brain. So we have a definite advantage in that we can look ahead in the game tree. But traditional medical treatment doesn't do that. It myopically tries to make the patient better off, which puts the treater at the same disadvantage as a disease. And now we have actually looked at how do we compute these policies that exploit the opponent's myopia. We're actually doing this on real simulators. So we have done this on a T-cell simulator for steering a patient's own T-cell population to battle cancers, autoimmune diseases, and infections. And we have also used this for cancer treatment cocktail and cocktail sequence optimization. And the last project I wanted to mention is search integer programming and automated algorithm design. So originally in my lab, we started doing search and integer programming for combinatorial auctions and generalizations of that. But now we're also doing it for general integer programming, constraint satisfaction, SAT, and so forth. So one of the interesting things that I like to think about is how do you branch? It's actually amazing that branching makes orders of magnitude difference in speed, but nobody knows how to actually branch. Also, we're doing various kinds of what I would call outside the box approaches. Like how do you restructure the search tree on the fly if you regret some of the branching decisions that you made earlier? And can we come up with some sort of a optimality certificate without actually doing tree search from the beginning of the tree? So can I somehow throw darts in the variable assignment space and then glue together a tree certificate or other kind of certificate of optimality from that, rather than having to make those tough branching decisions, which themselves are NP complete to do well, even approximately well. And then lots of other things on that vein. And then the last thing I wanted to mention is automated configuration of many aspects of algorithms. So we did the first large-scale industrial application of algorithm configuration starting from 2001 to 2010. We did $60 billion of winner determination in combinatorial auctions, where we were running these tuning algorithms that automatically change the algorithm parameters to make the algorithms faster. And more recently, we have the first algorithm configuration results with generalization guarantees. So the whole field of algorithm configuration used to be very experimental only. There was very little theory. And the risk is that you do well on your training set, but on your real problems that you face after that, maybe your algorithm isn't going to be fast or isn't going to give you good solution quality. So now we have these theoretically sound kind of pack-learned algorithm configuration approaches. First for integer programming branching, but more generally now also for other applications such as voting and sequencing problems in computational biology. And we have a very nice general theory that under very general conditions, we can do these type of algorithm configurations with generalization guarantees. So let me end there and take any questions. Thank you.
Thank you, Tuomas. Are there any questions?
I think the audience is completely on mute. Looks like.
They can unmute themselves.
Oh, they can. Okay, great.
Yes. I think probably given the time, we should probably take questions offline, and then let Faye get going on hers.
Sounds great. Thank you so much.
Thank you, Tuomas.